time doesn't tick the same way for everyone. In fact, it's stretched and squeezed in the vast expanse of space. Imagine astronauts aging slower than those on Earth, or a journey to Mars making you younger than your twin back home. This isn't science fiction, it's reality. Join us as we explore real cases where time moves differently in space, and discover how these mind-bending phenomena shape our understanding of the universe. Einstein's theory of relativity reveals that time isn't constant. It stretches and shrinks depending on how fast you're moving or how close you are to a massive object. Think of it like a rubber band. When you pull it, it stretches. In the same way, time stretches when you're moving quickly or near something massive like a planet or star. This effect, called time dilation, might seem like science fiction, but it's very real. Let's start with speed. The faster you move, the slower time passes for you compared to someone at rest. This isn't just a theory. It's been proven with precise atomic clocks on airplanes. When the plane lands, the clock has ticked slightly slower than a stationary one. The difference is tiny, but it's there. It's like the clock is taking a mini nap during the flight. Even at high speeds, like those in a sports car, time dilation happens. But the effect is so small that you'd never notice it in everyday life. Gravity also plays a trick on time. The stronger the gravity, the slower time moves. This is because massive objects like planets and stars warp the fabric of space and time. It's like placing a heavy ball on a trampoline. The ball creates a dip, and if you roll a smaller ball nearby, it will spiral towards the heavier one. Similarly, time spirals slower near massive objects. This effect is more noticeable than speed-related time dilation. For instance, a clock on the top floor of a tall building runs slightly faster than one on the ground floor. The difference is tiny, but it's measurable. This is why GPS satellites need to account for both speed and gravity when calculating our positions. They're moving really fast and are far from Earth's massive gravity, so their clocks tick differently than ours. Time flows differently in space, and this has been proven through various experiments. The most noticeable differences come from the effects of gravity and speed. Clocks on satellites, for instance, tick slightly faster than those on Earth. This is due to the weaker gravitational pull in space, which makes time move a bit quicker. Conversely, clocks on Earth move a bit slower because of the stronger gravity here. This difference, although tiny, is crucial for our daily lives. It helps GPS systems provide accurate locations. Without this understanding, the GPS signals would be off by several kilometers, making navigation much less precise. Scientists have conducted numerous experiments to measure these differences. One famous experiment involved placing highly accurate clocks on satellites and comparing them to identical clocks on Earth. The results showed that the clocks in space ran faster by about 38 microseconds per day. This might seem like a small amount, but over time, it adds up. For GPS satellites, this difference is adjusted to ensure accuracy. The satellite's clocks are set to run slightly slower to match Earth's time. Without this adjustment, the GPS signals would quickly become inaccurate. The effects of speed also play a role in time differences. According to Einstein's theory of relativity, time moves slower for objects moving at high speeds. This is known as time dilation. In space, satellites move at high speeds relative to Earth. This means that clocks on satellites would run slightly slower due to their speed. However, the effect of gravity is stronger than the effect of speed, so the overall result is that clocks in space still run faster. This complex interaction between gravity and speed makes the study of time in space fascinating. Understanding these differences is not just about scientific curiosity. It has practical applications. For example, in space travel, accurate timekeeping is essential. Astronauts and mission control need to synchronize their clocks precisely. Even a small error can lead to significant problems. In the future, as we explore more of space, this understanding will become even more important. The differences in time between space and Earth highlight the incredible complexity of our universe. They remind us that time is not a constant, but something that can be influenced by various factors. Time moves differently in space. This might sound like something out of a science fiction movie, but it's a real phenomenon. Astronauts on the International Space Station, ISS, experience this firsthand. The differences are small but measurable, and they have been studied extensively. Gravity plays a significant role in how time passes. On Earth, gravity is stronger than it is in space. This means that time moves a tiny bit slower on Earth than it does on the ISS. This difference is due to a concept called time dilation, which is part of Einstein's theory of relativity. It's like the universe's way of keeping time flexible. For astronauts, this means they age slightly slower than people on Earth. It's a small difference, but it's real. For example, after a 6-month stay on the ISS, an astronaut would have aged about 0.1 seconds less than someone on Earth. This effect isn't just a theoretical idea. It's been measured and confirmed. Scientists use extremely precise atomic clocks to track the tiny differences in time. These clocks are so accurate that they can measure the passage of a second over millions of years. The time dilation effect has been observed in many experiments, not just with astronauts. It's been seen in particle accelerators and even in GPS satellites. The difference in time can affect how technology works. GPS satellites have to account for this time difference to provide accurate locations. If they didn't, the GPS signals would be off by several kilometers. The aging effect is tiny, but it's an important part of understanding how space affects the human body. It's also a reminder that the universe operates in ways that might seem strange or counterintuitive. As we explore more of space, we'll need to consider these effects. They might seem small, but they can add up over time. For now, astronauts can rest easy knowing that they're aging just a little bit slower than the rest of us. It's a small perk of their incredible journey into the cosmos. Einstein's theory of relativity tells us that time isn't constant. It changes based on speed and gravity. This might sound like science fiction, but it's very real. It affects technology we use every day, like GPS satellites orbiting Earth experience time differently than we do on the ground. They're moving very fast and are far away from Earth's gravitational pull. This makes time pass slightly faster for them. Without adjustments, this difference would cause GPS locations to be off by several kilometers. To fix this, satellite corrections, or GPS adjustments for time dilation, are made. These adjustments ensure that the time on satellites and on Earth are synchronized. Otherwise, your GPS would lead you astray. A GPS satellite orbits at about 14 kilometers per hour. At that speed, time ticks a bit slower than it does on the ground. This is due to something called special relativity. Meanwhile, the satellite is also experiencing less gravity. This makes time tick a bit faster, a result of general relativity. These two effects compete with each other. The gravity effect wins out, making time pass faster on the satellite. Without correction, this would lead to location errors. Over just one day, the error could add up to kilometers. To prevent this, clocks on GPS satellites are carefully adjusted. They are designed to tick slightly slower to compensate for the time difference. This ensures that the satellite's time stays in sync with Earth's. The adjustments are incredibly precise. A difference of even a few nanoseconds can cause a position error of several meters. To put that into perspective, a nanosecond is 1/1000th of a second. That's like a drop of water in an Olympic-sized swimming pool. It's a tiny amount, but it's crucial for accuracy. GPS satellites use atomic clocks for their timekeeping. These clocks are among the most accurate in the world. They lose or gain less than a second in millions of years. Even with such precise timekeeping, adjustments are still necessary. Without them, the GPS system would quickly become unreliable. The importance of these adjustments becomes clear when you consider how much we rely on GPS. It's not just for navigation in cars or on phones. It's used in aviation, maritime navigation, disaster relief, and even banking. A small error in GPS timing can have big consequences. For example, in aviation, a few meters off can mean the difference between a safe landing and a dangerous situation. In banking, timing is crucial for transaction synchronization. A delay of even a second can cause problems. That's why satellite corrections are so vital. They ensure that our technology works as it should, keeping us safe and connected. Gravity is not uniform across the universe. It varies greatly, especially near massive objects like black holes. In these extreme gravity zones, time does not tick at the same rate as it does on Earth. This phenomenon is a direct consequence of Einstein's theory of general relativity, which tells us that gravity bends not only space but also time. Black holes are regions in space where gravity is so strong that nothing, not even light, can escape. At the heart of a black hole lies the singularity, a point of infinite density. As you approach a black hole, time begins to slow down relative to an outside observer. This is because the immense gravitational pull warps the fabric of space-time, causing time to pass more slowly in stronger gravity fields. For instance, if you were to watch a friend fall into a black hole from a safe distance, you would see their movements slow down and eventually freeze as they approach the event horizon, the point of no return. From your friend's perspective, however, time would seem to pass normally, and they would experience the fall differently. This time distortion is not just a theoretical concept. It has been observed in less extreme gravity fields. For example, satellites in orbit around Earth experience time slightly faster than we do on the surface due to the weaker gravitational pull. This effect, though minuscule, needs to be accounted for in GPS systems to ensure accurate navigation. In the extreme gravity zones near black holes, this effect is magnified to an extraordinary degree. Scientists have also observed time dilation in the strong gravitational fields of neutron stars, which are incredibly dense remnants of collapsed stars. These observations provide strong evidence for the theory of general relativity and its predictions about time distortion in extreme gravity zones. Time is a puzzle, especially when it comes to how we experience it. Everyone knows that time can feel like it's moving fast or slow. For instance, when you're having fun, time seems to fly by. But when you're bored, it can feel like it's crawling. This is because our brains don't experience time in a steady, objective way. Instead, it's subjective, shaped by our emotions, focus, and even our physical state. Think about a time when you were really focused on something, like a challenging task or a thrilling movie. You might lose track of time completely. This is because our attention influences our perception of time. When we are fully engaged, time can seem to pass quickly. Conversely, when we are waiting for something, like a slow-moving line or a delayed train, time can feel like it's moving slowly. This is because our brains are more aware of the passage of time when we are not occupied. Our emotions also play a big role in how we experience time. Strong emotions, whether positive or negative, can make time feel like it's moving faster or slower. For example, a frightening experience can make time seem to slow down, while a happy event can make it feel like it's flying by. This is because emotions can affect our brain's internal clock, which is responsible for our perception of time. Additionally, our physical state, like hunger, fatigue, or illness, can also influence how we experience time. When we are not feeling well, time can seem to drag on. Einstein's theory of relativity suggests that time can move differently depending on various factors, such as gravity and speed. This concept might seem abstract, but it has been confirmed through real experiments. One of the most famous examples is the Haffel-Keating experiment. In this experiment, scientists placed extremely accurate clocks on airplanes. They flew these planes at high speeds, both with and against the Earth's rotation. When they compared the clocks on the planes to identical clocks on the ground, they found slight but measurable differences. The clocks on the planes ticked a bit slower than the ones on the ground. This difference, though small, confirmed that time can indeed move differently depending on speed and direction. Another compelling example comes from the Global Positioning System, GPS, that we use every day. GPS satellites orbit the Earth at high speeds and experience less gravity than we do on the ground. According to Einstein's theory, both of these factors should affect the passage of time. Scientists have indeed observed this effect. The clocks on GPS satellites run slightly faster than clocks on Earth. If we didn't account for this difference, GPS would quickly become inaccurate. This is why GPS technology has to constantly adjust for these time differences. Without this adjustment, our navigation systems would be off by several kilometers each day. Scientists have also conducted experiments involving atomic clocks and high-speed trains. In one such experiment, researchers placed atomic clocks on high-speed trains and compared them to clocks at rest. The clocks on the moving trains ticked slightly slower. This difference, though minuscule, was measurable and confirmed the theory of time dilation. These experiments have been repeated numerous times with consistent results. They provide strong evidence that time is not a constant and can vary based on speed and gravity. This understanding has practical applications, from improving GPS technology to developing better space travel methods. The concept of time moving differently in space can feel deeply unsettling because it challenges our fundamental understanding of reality. On Earth, we experience time as a steady, consistent force. It ticks away at the same pace, giving us a sense of stability and predictability. But in space, this isn't always the case. Time can stretch or shrink depending on various factors, such as gravity and speed. This instability makes reality feel less tangible, more fluid, and harder to grasp. Consider the famous twin paradox. If one twin travels into space at near-light speed while the other stays on Earth, the traveling twin will experience time more slowly. Upon returning, they might find their sibling has aged more. This isn't just a thought experiment. It's a real phenomenon predicted by Einstein's theory of relativity. It's unsettling because it shows that time isn't universal. It's relative, and our perception of it can change based on our circumstances. This challenges our deeply ingrained notion of time as a constant, unchanging force. The idea of time being unstable also makes reality feel less solid. If time can change, then so can our experiences, memories, and perceptions. This can make life feel less predictable and more uncertain. It's like standing on shifting sand instead of solid ground. Moreover, it raises profound questions about the nature of existence. If time isn't constant, then what is? This uncertainty can be deeply unsettling, as it forces us to question the very fabric of reality. Yet, this instability also opens up fascinating possibilities. It allows for time dilation, which is crucial for technologies like the Global Positioning System, GPS. Satellites in space experience time differently than we do on Earth. Without accounting for this difference, GPS would be inaccurate. So, while the idea of unstable time can be unsettling, it's also a reminder of the universe's complexity and the need to adapt our understanding to its realities. As we've seen, time isn't as straightforward as we once thought. From the ticking clocks on satellites to the aging astronauts returning from space, it's clear that time moves differently up there. The next time you look at the stars, remember, they're not just far away in distance, but also in time. So, what other mind-bending facts about space are waiting to be discovered? Stay curious, and don't forget to like, share, and subscribe for more fascinating journeys into the cosmos. Until next time, keep looking up.